Hello.
It's hello.
Oh. Hello? Like that?
Hello guys, today we are going to talk about a new topic which is integer linear programming. You are all familiar with this part of the name, linear programming. We have seen lots of linear programs so far, and today we will focus on this part, which makes it integer linear program. Okay? So first, let's see what is the difference between an integer linear program and a linear program. On the left hand side here I have a linear program, a familiar form, maximization or minimization of a linear function subject to a set of linear constraints. And the main assumption in a linear program here, in addition to linearity of every function that I have, is that I assume that my variables are continuous variables. So in particular, every variable can take on fractional values. Okay? But when we talk about integer linear programming, of course, this term linear implies that still every function is a linear function of the variable, but I will have, in an integer linear program, I will have all variables that are required to be integers. Okay, so in a linear program every variable can take on a fractional value, but if in my problem I have some variables that have to have integer values in the optimal solution, then I am dealing with an integer linear program. Okay, and the term integer refers to the fact that some or all variables are required to be integers.
This looks new.
Think it's safe?
What is it?
In many cases, instead of saying integer linear program, people say integer program or simply IP. And the reason is that having integer variables in your model makes it a very powerful tool. Okay, its power is much more than linearity. So what I'm saying is that in many cases, if you have nonlinear functions in your formulation, we know techniques that you can introduce integer variables and form an equivalent integer linear program instead of a nonlinear program. So what I'm saying is that the power of this part is dominant. That is why in many cases, instead of saying integer linear programming, people simply say integer programming. Okay? So an integer program is a program in which is an optimization problem in which all functions are linear functions, and some or all variables are restricted to take on integer values. Let me add some comments. If all your variables are integers, then we usually call it a pure integer program. But if some of them, not all of them, but some of them are integer, it means that in your problem, in your program, you have a mix of continuous and integer variables. For that reason, it is called mixed integer program, MIP. Now, let me show you graphically what is a feasible region of an integer linear program. Okay? Of course, I have to do a two-dimensional work. So suppose I have an optimization problem like this, subject to ax less than or equal b, x greater than or equal 0. But in addition to this constraint, I also want x to be integer. And remember, x is the vector of variable, so in a two-dimensional space it is x1 and x2. So x being integer means I want both coordinates to be integers. Okay? So we already know that in a two-dimensional space, a linear program will identify a feasible region like this. And if it was simply a linear program, this area was my feasible region, every point in this area. But in addition, in here, in an integer program, in a pure integer program, I want every solution, every feasible solution to be integral too. So it means that a point like 1/2, 3/2 is not feasible anymore, right? So not every point in this region is a feasible point, only the integral point. So only the points that have integral values 0, 1, 2, 3, 4, only points that have integral values for both coordinates are feasible. So this one and this one, so this is a 5, 0, this is a 5, 1. These are not feasible, as well as every point like this point that is not integral in both coordinates, right? So I will have a discrete set of points as the feasible region of my integer linear program. Suppose this one is out, and so on. So the red points are the feasible solutions of my integer program, and that's it. Okay? So it's a discrete set. Every red point is feasible, and among them I want to find a point that maximizes my objective function. It is not a continuous space anymore. Okay? This is a pure IP. So every variable, here it was a two-dimensional problem, so x1 and x2 both had to be integers. Now let me look at a mixed integer program. What does the feasible region of a mixed integer program look like? So as I said, in a mixed integer program, some variables are integers, some are not. So let's say, for example, here I want x1 to be integer. So again, vector x is x1, x2. Now only want x1 to be integer. I don't have to specify anything about x2 because by default x2 is continuous. Okay? Now let's look at the feasible region of a mixed integer program in a two-dimensional space. X1, x2, and linear constraints. Okay, now a point like 1/1/2 is actually feasible, right? Because the first coordinate is integer and we don't care about the second one. The second one can be fractional. But a point like, let's say x hat, a point like x tilde 3/1/2, this point is not feasible, right? Because I don't care, remember, I don't care about the second one. It can be fractional or integer, it doesn't matter, but the first coordinate must be integer. Okay? So it means that as long as the first coordinate x1 is integer, x2 can take any fractional value, right? So if this is 1, x2 can take any fractional value, right? We will have infinitely many points in here. So actually the feasible region of this mixed integer program is composed of these line segments. Do you see that every point on these red line segments has its first coordinate equal to an integer, and the second coordinate x2 can have fractional values. Okay, obviously, like a graphical solution of a linear program, once you identify the feasible region of a mixed integer program or a pure integer program, you can use the same technique to find its optimal solution in a two-dimensional space, the graphical solution way. Okay? Okay, let me erase these. Okay, now let's talk about LP relaxation and answer the question that how useful is LP relaxation? Of course, we have to define the LP relaxation first. What is a relaxation? In optimization, when we say relaxation, we mean getting rid of some constraints, okay? So a relaxation means getting rid of some constraints. Remember that integrality of variables is a constraint. So we are enforcing some variables to take on integer values. So it is a constraint. And if I get rid of it, so if I get rid of integrality of variables in an integer program, I will get a linear program, right? And it is called the LP relaxation of my original problem. So associated with every integer program, you can form a corresponding linear program by relaxing integrality of the variables. In here, for example, you see that in this example, that xi, every variable, must be 0 or 1. Okay? Now I want to relax integrality of variables. Okay, remember that I just want to relax integrality of variables, not lower and upper bounds on my variables. I mean that what you have here simply says xi must be greater than or equal 0, less than or equal 1. Also, x1 must be an integer. Okay? I am relaxing this one. So I will still have bounds on my variables. Okay? Then this gives me the corresponding LP relaxation. What is the advantage of having an LP relaxation? We already know how to solve it. And actually, linear programs are the only general class of problems that we know how to solve efficiently, how to solve very fast. This is not the case with integer linear programs. The solution methods are completely different and very computationally intensive. So having a problem which is very similar to our original problem that we can solve fast is an advantage. But the question is, how useful is the solution of this LP relaxation problem? How can we use this solution? Okay? A very intuitive way to think about a solution of an LP relaxation problem is to say that, okay, I can solve the LP relaxation problem very fast. Let me do it. then I will get some fractional values for my variables probably. Okay, in that case I will round them up or round them down to get an integer solution. Okay, so something like this. If I relax integrality of variables, I will have an LP, then I solve it. Suppose I get this one, this extreme point as an optimal solution of my LP relaxation problem, but it is not an integral solution, so it is not a feasible solution to my integer programming problem. But probably this exists in between some integer solutions like this. Okay, and hopefully one of them, so these are not feasible, hopefully one of them, this red one, is a feasible and I can use it. Okay, there are a couple of issues here. First of all, you have to check lots of points to see if either of them is feasible to your integer programming problem. Okay, and don't think about a problem in a much higher dimensional space. This is a two-dimensional example. So in a, I don't know, in a 100-dimensional, 1,000-dimensional, a million-dimensional space, this is very time-consuming too. The other thing is that even if you are able to find some feasible solution around it, there is no guarantee that this solution will be an optimal solution to your integer program. Okay, so the solution that you get might be feasible, but there is no guarantee that it is optimal to your original problem. The other thing is that in many challenging problems, like the example that I'm showing you here, the solution that you get from the LP relaxation is not actually very informative. Consider the LP relaxation of this problem and try to solve it. Okay, then you will see that you will get X star, the optimal solution of the LP relaxation problem is this. Okay, so every variable takes on a value equal to 1/2. So you see that this solution actually gives you no information about an optimal solution of your integer program. Okay, so an LP relaxation problem, it is not useful in terms of finding the optimal solution of an integer program directly, so by some magical technique, but it is useful to getting an upper bound on the objective value of your original variable in a maximization problem. Since it is a relaxation, so you don't have some constraint, you will always get an objective value which is better than the optimal objective value of the original integer program. So an LP relaxation will give you an upper bound the optimal objective, so gives an upper bound on the optimal objective value of IP, but we cannot use its solution to get an optimal solution to the integer program. Okay, now let's look at some examples, some applications, how we can use this integrality of variables to model some real-world problems. Okay, our first example is the heavenly pouch example that you have seen before. I'm sure that all of you are familiar with this example. So a company is making two types of products, non-reversible carriers and reversible carriers, and we know information about the manufacturing cost, about the selling price, about the amount of raw material that each type of carrier needs. We also know the constraints of the limitations that the company has in terms of the raw material and the production budget. And we have formulated this problem to maximize its revenue, its profit actually, in terms of the variables x1 and x2, which represent the number of each type of baby carrier. Okay, this was the linear program that we formulated before. But the truth is, in reality, if you formulate a problem like this and you solve it and get a value like x star 1 is 23 1/2, it makes no sense, okay? Because x1 represents the number of product non-reversible carriers. Okay, so what does it mean that you have a 1/2 carrier? Nobody is paying for a 1/2 carrier. It is not functional. So naturally, x1 and x2 must be integers. Okay, this is the first application of integer programming. So in physical words, some of your variables must take on integer values. Okay, the simplest application and the most intuitive application of integer programming.